as well. And I am going to go ahead and share my screen. And it has also come to my attention that I actually can see the chat at the same time I'm sharing my screen. I just had to click a little button. So Dr. Reichel and I were having a conversation and she showed me how to do this and I showed her how to share her tablet. So never underestimate the power of telling somebody you don't know what you're doing. So although you have to do it you have to be careful. So I can see the chat. We are going to do an example of the homework in a moment, but there is a machining assignment that's out on Canvas, and we'll kind of go through some of those equations. We'll go through an example, and again, kind of talk about what we're looking at. So we left off on Monday at looking at the cutting tools, the materials. Oh, this is interesting. Okay. For machining. And so the requirements, as we can see, are like hardness, hot hardness, and then your toughness. Some applications you're going to need a little more impact resistance, and then also some of the chemical stability and wear resistance. So in looking at our tools, and as we go from steel to the carbide and coated tools, and then what we call the super abrasives, we're seeing that the hardness is going to be increasing and our toughness decreasing. So our metals, and that would make sense that the metals would have the higher toughness, but the lower hardness. And we also want to look at, as we go from steel to carbide to what we call the super abrasives, sort of the length of time that these tools maintain their hardness. So we're also seeing, as we go from one down, we see that the expected tool life increases as well. So does the cost. So I want to just spend a little bit of time kind of talking about the materials. So the steel and cobalt-based alloys, these would be our hardened tool steels. So these would be in that tempered martensite condition. We may have some additional carbides. I'm not writing anything down because this is not the course for us to get into the metallurgy of that. There are a number of what we would call, the carbide and the coated tools are probably the largest market share. And we're going to look at, when we look at the homework, on the homework PowerPoint, which we'll kind of move to in a moment, I actually have a picture of a configuration of a tool. A lot of times we have what we would consider to be an insert, and that is where we sort of have a carrier, and the actual cutting material is something that we can put in and easily change. So the reason that we might have coatings would, to some extent, go back to that chemical stability. So we might have actually an initial tungsten carbide, a submitted tungsten carbide, a CERMET, and then we might again put coatings on to help with wear resistance or chemical stability. And then our super abrasives, these are, these materials both have high hardness. And as we discussed, diamond, this can interact with steel because it's carbon. So this material, cubic boron nitride. So boron nitride is polymorphic, meaning it exists in more than one crystal structure. The cubic form of it has very high hardness. The hardness approaches that of diamond, but it has to be formed. So cubic boron nitride is something that is produced in a high temperature press in the same way industrial diamonds are produced in a high temperature press. And so if we're doing very, very high speed machining of steels, we would use cubic boron nitride. So my job prior to coming to MSOE, I worked for GE Super Abrasives, and we made both cubic boron nitride and diamond. So kind of a fun little thing going on there. But these are, again, these are tooling materials that have a very high hardness, and if used properly, we can have a long tool life, and we can look at high speeds. Okay, so if we look at tool life, there's a number of ways in which tools can fail. There certainly would be cracking. There's certainly going to be kind of a dulling of that. But there's a particular type of wear that's called flank wear. And the Taylor tool life equation allows us to get an estimate of the tool life for this kind of wear. And it kind of does help us sort out a little bit of the variables, because what we ultimately want is the settings that give us the lowest cost per piece. We have time, so the longer the time to machine, the higher the cost, but tool life has a cost as well. So in the simplest form, we're looking at, again, that's V times T to the N is equal to C. The weird thing is that T, capital T, is time. We're used to seeing time as small t, but here this is capital T. C and N are parameters for the tool and workpiece, and then V is the cutting speed. Now, we're going to really look at this when we do the examples and we start to get to the variables. There are, when we talk about feed and speed, there is that for the machine and there's that for the tool surface. If we, and we're all like, you know, all of us kind of understand that if you have if you have a piece that's rotating, that the actual velocity at the outside is going to be different than the velocity in the center. You know, and so we see the same thing with our tools. So the cutting speed here is going to be that speed, and it's going to be in feet per minute or inches per minute of the cutting surface with the material, which is different than what our spindle speed is. Okay, so N and C are related to the material. So let's look at, we have some, here's just a small table of some examples. Notice now our units get interesting. So if we look at what our equation is, if we kind of go back to our equation, we do see that we have C is equal to V T to the N, and therefore time is equal to C divided by V to the 1 over N power. So our, what we also notice is that our speed needs to be in feet per minute. So that's a calculation that we often need to do. So if I have a carbide tool on steel, notice that we can just by looking at the equation, machining steel is going to wear our tools faster than machining non-steel, so aluminum and non-ferrous. We also can see that if we have high-speed steel, so if I have steel tooling, my tool life is likely to be much lower. Okay, so I put this in, consider machining parameters. Now what I'm going to do is I want to switch to our homework and do some examples. So I'm just going to go ahead and move to our other. Okay, so this PowerPoint is out on Canvas, and it does have some helpful. Oh, I know what I was going to do now. Before we did this, I was going to quickly look at our, I'm going to see if I can do the quick video of some of our operations. Sorry about that. So I'm going to see if I can get, now I think a lot of us have probably seen machining operations, but let's, if I can do this whole thing. Well, let me see. Okay. Here we go. Okay, haven't started it yet. I think I have to, I'm going to unshare and then share again, because I think I need to do that to include the computer sound. Let's see about this. Why are you not playing? There we go.
In straight turning, the tool is fed parallel to the axis of the work to reduce its diameter so that the final diameter is the same at each end. Removing a significant amount of material in one pass is called rough turning. The final lighter cut that creates a smooth surface finish is called finish turning. Taper turning produces a taper along the axis of the workpiece. Tapers are produced by offsetting the tailstock from center line or by using a taper attachment. Short, steep tapers can be turned using a compound rest. Contour turning, or profiling, was formerly performed by having the single-point cutting tool trace a template of the desired profile shape.
I just think this is fun
This
to watch.
has largely been replaced by CNC turning, in which the desired contour is simply programmed into the machine, which directs a cutting tool to cut the contour.
So these are all these look
Forming
like
is
carbide
another
tools.
alternative for generating complicated shapes. The tool having the desired form or geometry is advanced perpendicular to the axis of rotation, reproducing the tool shape in the workpiece. Forming is commonly performed on automatic screw machines. Chamfering eliminates sharp corners from a workpiece and is a good safety measure. Typically, chamfering breaks corners at a 45-degree angle. Grooving creates a groove or recess using a tool that is usually the size and shape of the required groove. Some grooving tools can also widen a groove by traversing side to side after plunging into the workpiece.
Okay, so it's a real quick, just a real quick little operation or video.
Today I'd like to show you how to turn a square on a lathe. So what I have is a piece of material. In this case, it's 2-inch diameter and it's about 1 inch wide. I'm going to put it in a 4-jaw and I'm going to face one side, flip it.
Okay. I'm not really ready for the Oscars yet, am I? Am I for this? Okay, so, okay, I'm not hearing anything else. So again, when we look at turning, in turning, we have the part rotates. And so when we talk about turning, this is our this is going to be our speed. So anything associated with turning, so we see that the part rotates. So in turning, we talk about that as our speed. And then we see the tool moves into the part. And that is our feed. And we saw that in a couple different ways. We saw it moving in the very initial part, we saw it moving along the length, and that would be in straight turning. And then in the grooving, we also saw it moving into the part on here. And so let's kind of look at some of our variables and some of the things that we know versus what we want to determine and the symbols. So a lot of times it's just that. So when we talk about N is the rotational speed for our part. That's going to be in revolutions per minute. So whenever we see the capital N, that's what we're referring to. Now, we recognize that our diameter, the diameter, we also have our initial diameter, and I actually probably should put initial diameter and final diameter. So the diameter of the part changes as we're machining. The final diameter is, and I know that I don't mean to insult your intelligence by telling you like how the diameter changes, but we do see that our final diameter is going to be our initial diameter minus 2 times the depth of cut. And because the speed, that capital V, is related to the diameter, we do see in turning that the speed changes over time. So we talk about our part diameter, the initial diameter and the final diameter. We actually have 2 different feeds. So when the feed moves into the part, that is F sub R, so the axial speed of the cutter. But when we're actually looking at that cutting operation itself, we see that the feed is going to be an inch per revolution. So small f is inch per revolution. F sub R is the axial, is the speed of the cutter. NR is the nose tip, the tool nose radius. So it's basically how sharp is that tip. L is the length of the cut. D is the depth of the cut. And now if we look at some of our other ones, again, the ones down here, sometimes we're given. Some of the ones that we need to calculate in our homework will be the cutting speed. And again, our cutting speed is feet per minute. SFM is surface feet per minute. So if you're looking on a tooling website and you see SFM, that's surface feet per minute. Tools are often rated to a maximum surface feet per minute. And that is the one that is used in the Taylor tool life equation. Material removal rate, MRR, so that's just the volume of material per minute. The higher that is, the faster the operation. Our cutting power, that's going to be related to that specific energy, so it will vary material to material. And then we also have our cutting time per part, and that is our length of the part divided by our axial speed of the cutter. Okay. Now, this PowerPoint is out on Canvas if you're, and we're going to go through a set of calculations. Huh, well, this is interesting. Of course, okay. I don't know why it's not advancing for me, but let's see if, there we go. Okay, and I'm still sharing. So, in your homework, I want you to do a set of calculations for turning and for milling. And we have different conditions. And so for turning condition 1 from your homework, we have the following kind of variables. Our part diameter is 1.5 inches to start. So that's our initial diameter. Our rotational speed, so the part is rotating at 3,800 RPM. Our inches per revolution is 0.008 inches per revolution. We have a 1/64 inch nose radius. Our length of our cut is 3 inches, and our part diameter is 0.08 inches. Okay, so I am going to, here we go. So let's just kind of go through some of this. So first, let's look at our diameter. So our final diameter is going to be 1.5 minus 2 times 0.08, which is equal to 1.34 inches. And so our, might as well just go ahead and do our average diameter is 1.42 inches. So a lot of times we just go ahead and use average because we have to recognize that the diameter does change throughout the operation. So let's start with our speed. So our speed is equal to pi dn. So that's going to be pi. We're going to use 1.42 inches. And I'm going to actually, just for units, put in inches per revolution. And then I have n, which is 3,800 revolutions per minute. And we end up with 30.4 inches per minute. No, we don't. Of course, when I did this, okay. 1412. Okay. 1412.67. Okay. One should always make sure you remember how you did your calculation. Now, this is going to give me inches per minute. I want feet per minute. Now you can calculate inches per minute and then convert, but I need to know what and so I'm going to go 1 foot per 12 inches, and this is going to be 1412.67 feet per minute. Okay. So our next one, axial speed of the tool. Axial speed of the tool, that's F sub R, that is equal to Fn, and again, we're looking at 0.008 inches per revolution multiplied by 3,800 revolutions per minute. Here's the 30.4 inches per minute. Our material removal rate, this one's a little bit, So our material removal rate, this is going to be pi d average, depth of cut F n. Okay, so our good old pi, 1.42, again, inches per revolution. Our depth of cut, 0.000, 0.08 inches, 0.008 inches, 3,800 revolutions per minute. There, it's not the average, yeah. Okay, inches per revolution. So this equals 10.85 cubic inches per minute. And then if I multiply this by, then our power is equal to 10.85 cubic inches per minute multiplied by 0.3, which is what our specific power is. Because this is aluminum, that is equal to 3.25 horsepower. Okay. Yeah. So our next one, which of course be nice if I had managed my space a little better. Our next one, we're going to look at our tool life. So we'll kind of just look at that. And for this, we need to go back and we kind of remember our instructions tell us that this is a carbide tool. And so we have what our N and what our C are going to be. And we need that. I'm going to actually just use that we're 1412 feet per minute. So I'm going to just go to my next page and I'm going to look at, again, tool life is going to be T is equal to C over V to the 1 over N, and that's equal to our 2700, 1412 to the 4 power, and that's 13.35 minutes. So 13 minutes of machining time, and we're good. Cutting time per part. So our time to machine, so this is our cutting time. That's equal to length divided by FR. That one makes perfect sense. So we are 3 inches divided by 30.4 inches per minute. That is equal to 0.99 minutes. And then our, we could actually also get our estimated number of parts per machine, per tool as well. Okay. The other aspect of this is our surface roughness. So from the handout, and this actually comes from the ASM handbook, we have R sub I, which is our idealized surface roughness. So it's an idealized R sub A. This is equal to F squared divided by 32 NR. So this really tells us that for turning, the smaller the nose radius and the faster the feed, we end up with a rougher surface. So if I want to look at like what we have here, this is going to be 0.008 squared divided by 32 times 164, and this is equal to 128 microinches, 128 times 10 to the negative 6 inches. So again, none of these, you're probably like, none of these are really challenging in and of themselves, but it's important as you're kind of going through these to recognize the relationship between the variables, because that's really what we're kind of interested in. If I make the tool rotate faster, what changes? Does my tool life change? If I have a larger diameter versus a smaller diameter. So as you're going through these, we want to kind of think about how the variables change. Okay. We have the same thing with milling. I'm thinking that when it comes to milling, that maybe we'll wait either till tomorrow or kind of cover a few more things rather than just kind of, let's just kind of have turning kind of sit in our minds. But for milling, and again, in milling, what rotates in milling? The tool. So in milling, the tool rotates, and we see that generally the part moves into the tool. Okay. Well, I'm on a roll, so let me see if I can get my little YouTube milling to go. So again, we want to kind of think about the actual operation. So let me see if I can get this to function. I wonder if I can I make the screen bigger? Where's my stupid curve? Here we go. There we go. Oh, goodness. Okay, so let's look at a little bit on milling.
Milling edges, shoulders, and grooves may use a combination of end, peripheral, and/or face milling operations. Creating edges or edging may involve the milling of one or two surfaces. Shoulders typically have two surfaces.
So again, you can see that the part is moving.
Usually have three surfaces.
You get a little bit of an idea of what the chips
grooves
look like
may be closed at one end or open at both ends, and they may be cut on internal and external flat surfaces as well as on round surfaces. Peripheral milling cutters have cutting edges on their periphery, which are parallel with the axis of rotation. Peripheral milling is useful for creating long open slots and forms. End milling cutters are round shank tools with cutting edges on their periphery and end. The axis of rotation is perpendicular to the surface produced by the end of the tool. Cutter size is defined by its diameter and cutting depth. Since end mills cut more with the teeth on their periphery than with the teeth at their end, they are susceptible to lateral forces. This makes them subject to deflection, which reduces the accuracy of the milling operation. Short, shallow slots are often created with end mills. Deep, narrow slots may be milled with an end mill, a thin slitting cutter, or a grooving cutter. Grooving or slotting cutters are generally more efficient than end mills for cutting long and deep slots because of their larger diameter and greater number of teeth.
Okay, so I just really just wanted to kind of highlight a little bit on chip formation, the variety of some of the tools, and
Thread rolling is used chiefly to make externally threaded commercial fasteners in high volumes. Thread rolling is a cold forming process that uses two.
Here we go. Okay. So we could find out about thread rolling. That'd be kind of fun too. It's kind of like once I start looking at these things, an hour or so can go by and I'm like, whoa, and pick which one I want. So again, so in milling, we do have that the speed N is the spindle speed. So you'll notice that some of the equations are going to be the same. So if I look at the equation for cutting speed, which is again our capital F, it is still pi dn. The difference is the n is the rotational speed of the cutter, so it's still n. D is going to be the diameter of the tool. So the V and the N are a little bit different and pi's the same. You'll also notice that the table feed, and this is common, you'll notice that it has a small kind of a lower capital kind of a fancy V. So again, notice that we have the word feed. This is the velocity of the table. So in all the milling operations, you notice that the table was moving into the rotating part. Most of the time, the part is going to be rotating around the z-axis, but there was a situation where it was also rotating around the y-axis, but the part is still, the table's still moving in. So this is what we would call the table feed, and that's small v. So when we want to get our feed per tooth, which is F, we take into account the table feed divided by the rotational speed, and then we need to look at the number of cutting surfaces. So if we have a standard, you notice that they had the end mill, like, so you would just like count the number of cutting surfaces. Oftentimes it's 2. If we have a cutter, and if we look at, for instance, one of the cutters that we're using in the example, we actually have 7 inserts that are on the cutting tool. So in this case, we would have 7 cutting surfaces, and for the end mill, we would have 2. Oh, what did I just do? I don't want to do this. Okay, here we go. So we can kind of get that. The time, so the cutting time per part. You also may have noticed that when you're machining, you're starting to cut prior to the tool being all the way over the machine, of the part, and then there's also some overshoot on the other side. So when we look at cutting time per part, we include the length of the part or the length of the cut, plus we always add some overshoot. The overshoot, you can start to get kind of complicated with exactly how you calculate that. There are some rules. In general, we would just use the diameter of the cutter. So assume that your overshoot is half on the entrance and half on the exit side. If we have to do more than one pass, so for instance, if we have a 1-inch cut and a half inch cutter, we are likely going to make 3 passes, and so we just sort of divide by that. So that just kind of makes these a little bit different, but we could go through the same process. I am not, because we might, tomorrow I think in class I'll kind of briefly give us the final results on these, but we could go through that same kind of example. Again, there's going to be 8 combinations for milling, and we've got those, and we'll look at surface roughness as well. We don't, there's not quite the nice calculation for surface roughness in milling as there is for turning, but in general, we see that feed is really more important, whether it's the table feed or the tool feed. Feed tends to affect surface roughness. Okay, so let's go back to what we were talking about for the rest of today. So we've kind of considered some of our parameters, and let's look at sort of our general overview. Temperature. So I think anybody who's been involved in machining, you recognize that as you machine, things get hot. And we sort of talked about the areas where we can see this increase in temperature. So we're interested in the workpiece, the chip, and the tool. We would actually like for the tool to not get hot, because the higher the tool temperature, the shorter the tool life. So we would like to minimize the temperature increase, because this affects tool life. The hotter the temperature, the higher the temperature, the more the tool life is going down. We would like to keep lower, and again, this is due to, we'll call this surface integrity, because we don't want, we don't want to start heat treating our surface, and so we would like, it is okay if the chip gets hot. So if we could send all that thermal energy into the chip, we can. We would like that. So we do, again, you may have noticed that there's a lot that in almost all of the examples that we saw in those 2 videos, there was going to be some sort of coolant. You also sort of noticed that in some cases you may have multiple jets of the coolant. Sometimes air is used, but usually it's going to be a liquid. Again, cutting speed and depth of cut, these are the primary variables associated with tool temperature. So I'm going to just sort of put a note here. Feed influences our surface more than temperature. So if we want to have, so the feed will influence our achievable surface. It doesn't influence temperature as much. So again, when we're kind of looking at trying to maximize efficiency, we do need to kind of, again, think about our variables. Well, cutting fluids are really important. Almost all machining should be done with some sort of cutting fluid. If you go talk to Roger and he goes to machine something, he's likely to there's a pot of oil, and he's often going to brush oil on either the part or the tool. And that's, again, that's our cutting fluid. It's going to reduce friction. It's going to lower temperature. So usually they're going to be, kind of thermal conductors. They tend to wash away the chips. So you notice that in a lot of those examples, the chips were sort of nicely coming off, and they protect the surface. So we need to kind of realize that we create a fresh surface in machining. So there is no oxide to start. Yeah, so there's no oxide to start. And so we would really prefer that we don't machine and rust at the same time. We're not really going to talk about cutting fluids in great detail. I think it's important to recognize that some of the older and less automated are basically going to be just some sort of oil. And mineral oils are very common. Sometimes you may have an additive. Those are not used as much in our higher production. We tend to go with more water-based fluids, and there's just these oftentimes are likely to be created with environmental considerations in tow or in mind. We're usually, hopefully, having in our machines recirculating so that you're not necessarily like using and discarding. If you're sort of thinking, well, then if we have fluid that's sort of sitting around, you may also have some things in those fluids to prevent mold from growing. And so we do sometimes see that your fluids are likely to be slightly different. I see the biggest difference in cutting fluids between cutting metal and cutting wood. You usually don't want to kind of combine those two. But I think to realize that we almost always are going to have cutting fluids in our process. Okay, so to just sort of finish off this particular section, if we kind of look again, if we go back to our variables that we're interested in, we're going to be interested in surface roughness. And again, our surface roughness is related to the feed and the tool. It could be the tool radius, it could be the tool diameter, but we see that surface roughness is very related to feed and tool geometry. The tool life, again, that's more related to speed. Certainly tool material and workpiece material as well. So we see that, and our calculations may show that. Our dimensional tolerance, and this I think we will chat a little bit more about tomorrow, as our book kind of highlights, fixturing, tool selection, and sequence of steps all influence the tolerance. And as we had in our reading assignment, we really want to minimize bending and elastic deformation. So I think that tomorrow we will cover, we'll kind of go over some of the examples on tolerance, wrap this up, and then we will start on the alternatives to additional material removal processes. So I don't think I have those PowerPoints up yet, but I will put them up. So, okay. So I think this will call it a day. And let's see.